But so it's generic. They get all those things. Yeah. Yeah, they grow a lot of chilies. And
Chili.
they just grow the small ones.
Yeah.
Yeah.
¿Quieres mucho? ¿Quieres? Está hablando.
¿Alguien está hablando? Shadow.
Okay.
No sé, vaya, está bien. Pensé que él estaba en el Zoom. Está hablando.
But sometimes they do make those sound good.
Ya vengo, voy al baño.
Nervios de última. Se hace la picha.
Then we spice it. Now, oh yeah, it's just nice if they don't go sitting on the floor. Oh yeah, yeah. It's hard to make this. Ice cream is not good. That's because you know, a lot of people here. I think they make you. No, that's not. They sell Pepsi, Sprite. They sell. That's the right. Yeah. But I
Hi everybody. Hello. Is everybody here? Yes. We missing somebody? Yeah. Okay. Well, today we have for the afternoon 3 presentations. After that, I will give you homework. Oh, you need to do homework. Yes. Yeah, it's about how many questions we have on that homework?
12.
Okay, 12. 12. Yeah, 12.
MCQ or what? MCQ? 12 equation. As a MCQ?
MSQ?
Yeah, multiple choice.
No, to write.
Yeah, some of them, and the other you have to write for each question 2-page report. Something like that. Yes.
24 page, it's good. Tomorrow I am absent.
Yes.
I will be sick.
And
Yeah.
tomorrow we are giving the certificates also.
I will come tomorrow.
Tomorrow is the ceremony for certificate.
Yeah. I will be.
You can stay at home tomorrow, but you will miss your certificate. Okay. Well, this afternoon is about presentations of the students' work. All of them you will see are related to remote sensing, and all of them are different. So feel free to ask questions. The projects are differently scoped to. Some of them are in urban areas, others are with drones, others are with satellites. So feel free to ask questions and see if any of this information might be useful on the research that you are also doing. Okay. We're going to start with Karen Mesa. You already know her. She's working in urban areas where the application of drones for evacuation transportation, it has been quite minimal. So her work is opening the path of using this technology in uh, cities. So, Karen, they're all yours.
Okay.
Just a question, is this presentations will be shared with us or?
We could share that. Yes.
Okay. Today I will show what I'm doing during these 3 years. This is my 3rd year as a PhD here at USU. And first I would like to introduce why I'm doing this research. Okay, is it working?
Give your voice.
Okay. Do we have
Shout
mouse?
as well.
Mouse? Yo tengo. Okay, now it's working. Today I will show what I'm doing in my research. Can you hear me in the back? Yes. Okay. I'm working in urban areas, as you see in this main picture that I took with a small drone that you saw this in the data collection in the previous days. What I'm doing my research in urban areas, there are some motivations. When you are doing or conducting a research, first of all, what we need to do is what are the motivations to start a research, or what are the motivations to collect data, or what are the motivations to do this research in a specific location. Because later when I'm writing my proposal for my thesis, there is a specific format that I need to explain my committee what I'm doing this research. In this research, I identify 3 motivations. One is, as I'm doing my research here at United States, I'm identifying what is the areas that we need to pay attention regarding to water scarcity and climate change. One important area or sector is agricultural areas, but another sector here at US is these urban areas. And part of these urban areas are covered with urban turfgrass. Urban turfgrass, sometimes people cannot identify as a beneficial crop, because if we talk about agricultural areas, we said food security, we are concerned about potatoes, corn, do studying corn and potatoes fields. But here or in other cities that are populated, urban turfgrass provide a lot of benefits. Some of them is recreation, some of them is aesthetic, some of them is functional, and some of them is environmental benefits. During pandemic, if you remember, we are all at home. We couldn't go outside, but we probably most of us, we got stressed at home without going to the park or to see other open areas. In many scientific articles said that these urban spaces as parks, athletic fields, and other similar are so important for our health. So, as US has many golf courses, parks, athletic fields, homeland, if you see 60,000 golf courses, a lot of area to do studies. Another motivation is water scarcity. In this picture, you can see clear how this urban spaces has been affected because of water scarcity. There are some restrictions, like in this urban sector, we have water that goes for irrigate these open areas like turfgrass or our potable water for the population, and they prioritize in urban areas where to irrigate or in what areas we need to irrigate. As I'm doing my research in golf courses, in this plot, you can see how the applied water per acre has been decreasing in these areas. And in some articles, they said that because of this decrease of water, they are closing some golf courses, or they are trying to remove turfgrass and trying to plant another plant materials that consume less water. But still, turfgrass is one of the main things in these golf courses. You cannot replace turfgrass with other because it's part of the game to have turfgrass in the fairways, tees. Water consumption. As I'm mentioning, why is important turfgrass in urban areas? Why water scarcity is affecting these spaces? We need to check water consumption, because water consumption is telling us how much we need to irrigate. As water consumption, I'm defining ET, evaporation plus transpiration. Previous days in this workshop, you know why we are studying evapotranspiration and why it's important, this component in the water balance. Now, what are the challenges in my research? As I mentioned, 3 motivations. I have some challenges in this research. One is the spatial heterogeneity. If you remember, last week, we ran TCEP in alfalfa field. This is a homogeneous area, and it was kind of easy for us to run the model in alfalfa field. But if you see this area, the golf course, you have many classes. You have turfgrass, you have trees, different sizes, different shapes. You have sand traps, you have sidewalks, you have a swimming pool, you have a parking lots, you have buildings, and other classes too. For the two-source energy balance model, using satellite information will be difficult to identify these classes, turfgrass and trees, because I'm estimating evapotranspiration. Will be difficult because of the course resolution. Here is an example of different classes that I have in my research location. And as I mentioned, satellite data will not help to identify turfgrass and separate from trees and sidewalks, for example. Another challenge in this research is leaf area index. Do you remember what is leaf area index? What is? Yeah, leaf area index. What is leaf area index? Yeah, LAI.
The equation of leaf area index.
Why is important in the model? Remember, in the two-source energy, it's an indicator of biomass, right? Because if I have high values of leaf area index, the rates of ET will increase too, right? Now, how to estimate or measure leaf area index in this short turfgrass? Any ideas how to do? Can I use this sensor?
No.
Any ideas that you can help me in my research that I can apply? What?
Put your hand and see how many.
By weight, I think.
Weight?
No, the drone used the equation, but it doesn't measure or it doesn't give us the one. So how she can estimate LAI in turfgrass?
You need to buy image analysis, digital image analysis, can we cover?
But how? how to do the
Yeah,
digital.
sometimes you take digital image, but with certain criteria, okay? And to crop the image is just to the center of the image and try to calculate with some processing on some computer models like ImageJ, for example. This is one simple and the application online. And then you can measure the canopy cover. There are some equations that can relate between canopy cover and leaf area index, but I myself, I work with canopy cover directly.
Yeah. First, I try what are you saying. I took images and then to run the software ImageJ and to get the area. But you have many layers here and the turf is combined. The leaves are mixed. I will show later what I did to estimate leaf area index, but this is one challenge. Now, I have my 3 motivations to conduct this research, some challenges in this research. Now comes my research questions. What I'm doing in my research. If I'm planning in this research to estimate evapotranspiration using the two-source energy balance model, I should validate these results. My first research question is, what are the daily actual evapotranspiration for irrigator grass over the summer irrigation season? How to measure evapotranspiration? Do you remember we talked about the first day or second day of this workshop, how to measure evapotranspiration to validate our remote sense ET models?
Many methods.
With what?
There is 3 methods, maybe energy balancing method like this to compute ET.
TCEP is based on energy balance,
Yeah.
but how to validate my results?
So balance.
Huh?
No, using.
No? Huh? How?
Penman method. Which
A hint is an instrument. What instrument I will use?
lysometer.
Could be,
Yeah, but lysometers.
Yes.
yes. But what other sensor we saw in the first day of the workshop that can validate eddy covariance? Okay. As Larry Hibbs is my co-advisor, I have an eddy covariance tower in my research study. That is the instrumentation that I use to measure evapotranspiration. Okay, that is the first step. That is my first research question that I need to answer. What are the evapotranspiration for turfgrass in the golf course? Second question, how to quantify leaf area index, right? Because I need leaf area index to run the two-source energy balance model. But also, in this golf course, I have turfgrass and isolate trees. How to estimate leaf area index in these isolate trees too is part of the second research question. And the last research question is, what is the accuracy of hourly and daily estimates of evapotranspiration using the eddy covariance measurements and the TCEP results? I will validate and compare what is the accuracy of TCEP results. In this nice picture, you see I'm using drones, I'm using the eddy covariance tower, I'm applying the two-source energy balance model in my research. Now, let's move to the study area. This is the golf course where I'm doing my research, 20 hectares. And here you can see the land cover classification. We have turfgrass, 90%. We have some isolate trees. We have sand traps. And non-turfgrass are related to buildings, parking lots, sidewalks, and similar class. In this golf course, they have a sprinkler irrigation system. They use secondary water for the irrigation. And in this red dot, I have the eddy covariance flux tower. do you remember Larry said how to, what criteria do we need to take to locate a eddy covariance tower? Do you remember? What criteria do we need to know in order to install an eddy covariance tower in our research locations?
Search for prevailing wind direction.
Direction, wind direction. Find a predominant wind direction, wind speed.
Yeah.
Another. Have a homogeneous area. Do you remember? An homogeneous area. Another. Temperature? No, I think the main is wind speed. Wind speed,
Direction,
Wind direction.
wind direction,
footprint,
snow, no. Another criteria?
تحسب الفاريانت تشتغل
variance.
homogeneous.
Canopy height. Do you remember? If it's a forest, if it's a tall grass area,
Height,
canopy height. Okay, three things. We should have an homogeneous area. We need to find the record of wind speed and wind direction. And we need to know what canopy is around the tower. If it's tall grass, we should consider at what height we need to put the sensors of the instrumentation. And if the wind direction is saying to the southwest, I should have homogeneous area in that southwest. In the homogeneous area, sorry, if the wind speed and wind direction said north, I need to have the homogeneous area in the north area. That's the reason here is the tower in this red dot. I have this homogeneous area to measure evapotranspiration. Okay. What do I measure with eddy covariance tower? The four components, remember? Someone in the first day said net radiation equal to latent heat flux plus sensible heat flux plus G. Do you remember this equation? I measure all these components with this tower. But what is the frequency? 20 hertz. What is the meaning of 20 hertz at 20 hertz?
500%.
20 values per second.
Yeah, so
Okay. Now, in this figure, you can see the sonic anemometer sensor that measures wind speed in 3 directions. And you see the infrared gas analyzer sensor that measures water vapor and CO2. In this other picture, we have the net radiometer. I have net radiation, latent heat flux from these two sensors, sensible heat flux from these two sensors. How to measure ground heat flux? In this other picture, I have a data logger that collects soil moisture, soil heat flux, and soil temperature to estimate G, soil heat flux. Okay, this information will help to validate the two-source energy balance model, because if you remember, when we ran TSEP, we have the same components. We have net radiation, latent heat flux, sensible heat flux, and ground heat flux. This is from TSEP, and this is from eddy covariance tower. Now, to run two-source energy balance model, I need to create the inputs. As you create the inputs with Anderson, land surface temperature, leaf area index, ground cover, green fractional cover, weather data, and other parameters. For me, I'm using this camera, Altum camera. I'm collecting these 5 multispectral bands and 1 thermal band. I will use the thermal band to create the land surface temperature map, and these multispectral bands will help to create leaf area index that I will show later. Why I'm flying drone at this height? 120 meters. Why not 30 meters? Why not 60?
Because this is allowed by the law.
The maximum?
Exit precision.
The flight height is related with the spatial resolution of the data that I will get, but also an important consideration in urban areas is to check what the Federal Aviation Administration allow us to, at what height we need to fly. Okay, that is important in urban areas. But in agricultural areas, I think there are more range of flight height. Now, you know what is two-source energy balance model because you ran this model. But in my research, I'm running 2 times. Why 2 times?
Because bright of trees and grass.
Yes. I have trees and I have turfgrass. I have a protocol how to measure leaf area index in trees. As you see here, I'm using the leaf area index sensor. I did a 3D reconstruction for the post-processing for LI in trees. In turfgrass, what I did? It was intensive work to collect leaf area index for turfgrass to validate the model that I'm proposing. What we did, we went every time when we were flying drone, we collect turfgrass leaves. We use this sampler and we cut leaves for this sampling area. We collect all these leaves in these plastic bags. We put in the cooler and we came to the lab to clean all the leaves, to use a scanner to scan the area of the leaves, and to use a K-means classification approach to get the area of these leaves. As I'm getting leaf area index, ground data, this is called a destructive method. You go to the field, you cut the leaves, you know the sampling area, and you can get leaf area index. This is my ground data using a destructive method.
How did you measure which area?
Okay, camera.
Okay. I can explain here. Okay. I use this sampler. In this picture, you see this sampler. I have a chunk of turfgrass. We cut the leaves. And then we put in the plastic bag in a cooler. And then in the lab, we use a scanner and we put all these leaves here. We scanned and we have as a result a file JPEG. And I use a K-means and supervised classification model. And I got the area of the leaf, or area of leaves. This is leaf area index called the destructive method. Now, I got like 200 samples, but every time when I go to fly drone and collect data to run TSEP, I should have a leaf area index map. For that, I create a linear regression, leaf area index, ground data, spectral vegetation indices. I create a list of spectral vegetation indices to see which spectral vegetation indices will predict leaf area index. And then I create the leaf area index map. I will show what results I got in the next slides. Now, something important when we use eddy covariance tower is to check the energy balance closure. What is the energy balance closure? When we are using eddy covariance tower, I said we have net radiation, latent heat flux, sensible heat flux, and ground heat flux. Net radiation should be equal to the sum of these three components, but in reality, it's not the same for any reasons. Now, in order to see the performance of our results from this eddy covariance tower, we should see the energy balance closure values. It's called ABC. If you find articles, you can go in deep what is energy balance closure, but in summary, we'll say, if your values are below 0.7, this data is not reliable. But if the values of energy balance closure are about 0.7, values of eddy covariance measurement are reliable. And we should use these values for the validation of the two-source energy balance model. This energy balance closure is an approach to verify how our flux measurements are part of this energy balance. Now, after doing this checking of energy balance closure, these are the values of evapotranspiration, millimeters per day for 2021 and 2022. I will use these values to validate the two-source energy balance model. Do you remember in alfalfa what values you got? How many millimeters?
I think between 5 and 7 millimeter per day. I think.
Yeah.
5.7 millimeter per day.
Yeah, a way to validate if 6 or 7 or 5 is correct is using this data. To find, for example, September 1, how was the ET? And you know, oh, it was 4. Okay, how was the ET?
It depends.
And you can validate, say, okay, the model is performing well. Or you can say, the ET measure was 4, but the TCEP said 2. Something is happening because you have 2 millimeters less. Okay. These are the results for the estimation of leaf area index using multispectral data. From the list of spectral vegetation indices, I choose these 6 spectral indices, as you see here, and I decide to use who has less root mean square error for the TCEP model. But at least I choose 6 of these spectral vegetation indices. These are the 2 equations that I found to predict leaf area index for tallgrass. If you see, near infrared band and red edge band help us to predict leaf area index. Do you remember why these 2 bands are important in plants? Near infrared and red edge. Remember? Remember this? Red edge and near infrared. This is the spectral signature for vegetation, right?
Yes.
Well, red edge and near infrared, in my research, help to predict leaf area index in these two equations. Okay, results. As you got your results from TSEP, also I have my results from TSEP. First, the inputs, leaf area index map, land surface temperature map, fractional cover map, and green fractional cover map. All these maps were created using drone data. Now, for the hourly energy fluxes, because the first time when you run TSEP, you have hourly results. And later, using the ET daily formula, you get a daily ET. But from TSEP, you have hourly energy fluxes results. Only, I think you saw latent heat flux, but we have ground heat flux from TSEP, sensible heat flux, and net radiation from the TSEP results. Now, latent heat flux, this hourly data we use to estimate daily evapotranspiration. Now, how to validate the two-source energy balance model? This is important. I think we have not explained too much about footprints. Or do you remember about footprints, flux footprint model? How to use the flux footprint model? Or how to create?
When did you explain?
No, I'm asking, probably we didn't explain, but I'm asking if you remember. I think we didn't go in detail, but now I can explain how to use the flux footprint model. We have these results from TSEP, right? And you saw this for all the cases that you have. Now, how to validate this map with the eddy covariance measurements? Remember, the tower is located here. Do I average around the tower, the pixels around the tower, and compare with the values from tower? What do you suggest, or any thoughts? How to validate the TSEP results with the EC measurements, eddy covariance measurements? Because this is the map, and I want to validate. If someone say, okay, you went to US to learn remote sensing to estimate ET, now how to validate these ET results? What you will say? Or we cannot validate? Or what do we need to validate? Okay, this is the question. What do we need to validate these maps?
What about drone data?
Yeah, this is the results from drone and TSEP.
Okay.
Yeah, this is the result. And how to validate these results? Yeah, eddy covariance. Plus what? Because eddy covariance is here. The measurements are here located. But what do we need?
Geospatial analysis? What about land surface temperature?
We use land surface temperature for the TSEP model.
Yeah.
We need the
measurement of the leaf area index.
this is eddy covariance. We need the flux footprint model.
Flux footprint
Model. This is LE. Remember? Latent heat flux. Here is the tower, the EC tower. The measurements that I have here are time series, right? Time series. This LE is a raster, right? And this is time series of LE. Now, here, eddy covariance measurements plus the footprint model will validate this latent heat flux map. How to create a flux footprint model? Well, it's called KLU model. There is a paper where they explain how to create this model. And what is the footprint? This is the footprint. This is the footprint for the validation. How to create the model? The flux footprint model. I need data from the eddy covariance tower and other parameters to create this footprint. Now, having this footprint, the TCEP result, and the eddy covariance measurement, I can validate the TCEP results because I know from what area the fluxes are coming to the tower, and the tower is measuring for that specific hour. Because when you run the TCEP model, you run for the hour that you flow the drone, right? Could be 1 p.m., 12 p.m., 2 p.m. For that specific hour, you should create this footprint. This footprint is hourly footprint, and this helps to validate the TCEP results. Now, when you validate, you have data from two-source energy balance model, and you have data from the tower. And you can see how is the performance of the model. In this case, I have 4 data sets. For example, latent heat flux, 4 or 5. I think 5 data sets. 5 times that I ran TCEP. And I'm checking TCEP results with eddy covariance measurements using the footprint area. Now, this is important. We want also to know daily evapotranspiration and what is the performance of TCEP for daily estimates. There is called a daily footprint too, and the daily footprint has this shape. Why the daily footprint has this shape? Do you know? Wind direction, because wind direction is changing during the day. And this footprint could be for 10 in the morning, 11, 12, 2, 1 p.m. And you generate a daily footprint. And you know this equation, you used to estimate ET daily from instantaneous latent heat flux. If you remember, you use this equation. In summary, I just validate the two-source energy balance model for the golf course. And last week, I submitted my first manuscript. I'm so happy because I put all these efforts in this manuscript and all the validation for the two-source energy balance model in green urban areas and how to use the eddy covariance system to validate the model, how to generate the hourly and daily footprint, and what other considerations we need to take for running TCEP in green urban areas. Thank you. Yeah, this is all from my research. I'm still working for the second objective, second manuscript.
Until now, you didn't finish your PhD?
No, this is my 3rd year.
Yeah.
More work.
Quiz, a rapid quiz. What is the footprint? Yes.
I want to ask about footprint. Was did she get some random footprint or
No, it's never that. Okay, this is especially since there is a tower in Egypt, right? Icarda has a tower. It's important that you understand the concept of footprint. Okay, imagine that I have a farm, any shape. Okay. I need to put the tower, those instruments in the field. I want this to be my validation site. So I will put it probably near the center. So I have a tower like this with the sensor that will receive the water vapor brought by the wind. Okay, so here is my easy tower. Okay, now this will be okay. This will be okay. What the criteria to put a tower is the wind direction. From where most of in the year, what's the prevalent direction the wind takes? So the wind could come this way, or come this way, or come this way, or come this way. All right. I need to know historically what's the major wind direction. Okay, let's say it's this one. Okay. The second thing that I need to know is how strong is the wind? How many meters per second occurs in this area? Why? Because the stronger the wind, the more area the wind will use. Let's say I have a very strong wind. So the wind will bring water vapor from a larger region to the sensor. It could include the agricultural area or outside. Or if the wind is low, it might bring a smaller area. So before putting the tower, I need to know from where the wind is coming, how strong is the wind, because if it's the green, the average value or the highest values of wind in this location, then what I need to do is to move this tower, right, to this new location. Okay. So I will have a large footprint, but only from the farm, not the outside, because the outside I can have nothing, like an arid area, or I can have buildings, or I can have another crop. The assumption, the major assumption for an eddy covariance is that the footprint, the region that from where the sensor get the water vapor is the same crop and it's uniform. So I cannot have treatments. It has to be all of that, the same type of crop and the same management. So that's the criteria, the fundamental criteria to put a tower. Okay, so in Karen's case, in front of the eddy covariance tower, there is just this uniform grass area. There are no trees in this area. The trees are outside. Here is the tree, here is the tree, but none of them are in the footprint. We need uniform, and in her case, it's grass. So, how we use now the eddy covariance, the footprint. Okay, how do I use the footprint to validate TSEP? You already calculated TSEP, right? Okay. So this is, let's say I flew at solar noon, 12 p.m. And at that moment, the eddy covariance also has a number for the 4 components: radiation, latent heat flux, sensible heat flux, and ground. So this is my map. And I mathematically, there is the model called by A. June et al. I think it's 2020. A. June. Okay. This perimeter is a mathematical model that says all this area has influenced the values measured by the sensor. Now, I have my map, and when I have my map, I got pixels, right? I have my net radiation, latent heat flux, So I have pixels that are within the footprint, right? So what I'm going to do is I'm going to extract the pixels inside the footprint. Okay, I'm going to take them out, and I'm going to do sum them. Okay, pixel. The pixel could be net radiation or latent heat flux or H or G. Because this give me all these energy balance components layers. So per layer, I'm going to do the sum, but there is a trick. This mathematical approach, this mathematical perimeter has weights. The weights are like contour curves. Higher weights are toward the sensor, lower weights toward the edge. So let's call the weight W. So I'll have the weight of the pixel times the pixel, and I will sum them all. That is my total net radiation DSEP, LE DSEP, and I will compare it versus eddy covariance of net radiation eddy covariance. So the figure that you should show that we do the one-to-one graph when we say LE, no, we say eddy covariance DSEP, we plot all of them. We're going to plot the net radiation values. We're going to plot the LE values. We're going to plot the G values. We're going to plot the H values. The value that I get from this mathematical calculation for DSEP and the value coming from the tower. So these values are expected to be around the 1-to-1 line. If the model is working, all the components are along this line. If it's not working, if my H happens to be here, or my LE happens to be here instead of the 1-to-1 line, there is an issue with the model. This is how, so we can calculate R square, root mean square error, but for us, this is the most powerful way to see all the components matching the tower. When we do eddy covariance, we validate 4 values, G, H, LE, and net radiation. When we do lysimeters, we only validate 1. We validate only ET, right? So this is something extra benefit that brings you the tower. You're validating 4 values, 4 different values. So you can, but when lysimeters, you validate only 1 value, the ET. So this is the mathematics or behind the curtain of how we use the eddy covariance. So for example, if I were to talk with Card about their tower, I would say, where is your tower? Because what I want to see is that in front of the tower, there is this uniform probe happening. If I have a tree in the middle, I'm like, maybe we need to choose a better spot. And that's okay. Eddy covariance towers are very portable. We can move them. we can move them to another location where we don't have that interference. So that's when we say, okay, but maybe there is nothing and the location is really nice. And we say, this is high quality eddy covariance data. We can run all series of experiments here. That helps? Okay, that's the science behind the eddy covariance. This weighted curve comes from a paper that then we use to do this weighted sum that will give us values to compare it against the eddy covariance. And if they fall into the one-to-one line, we say we're done. We finished our work. Questions? No. All right. Thank you very much. Yes, question? Okay, I think we can continue now our
Can we
present.
make 5 minutes?
You want 5 minutes?
Just a 5-minute break,
Okay,
if they will.
5 minutes, it's okay. All right. Yeah. Get,
Just 5 minutes.
yes, okay.
Just 1 second. I have a. You use this one?
Yes. All of them. All of them.
All of them?
Yes.
Yes, I get this one and this one.
Yes.
And this data from.
Yes. So we compare 4 values.
4 values from
Yeah, 4 values.
from this and from this.
Yes.
We're gonna have a little bit of get together and say, yeah.
Pues no hay mucha relación entre los tres.
Yeah. So that'll be, yeah, they got.
Ese producto, ¿qué por esto que qué tan grande es? Porque 60 minutos.
Our piece.
Oh, yes.
It's good that we share the was alarm.
Yeah.
It's important day.
All right. Yeah.
Thank you. رجالة هم الأربع. يوم الأربع.
Yeah, so we can go after last days. You have your stuff with you.
Sí, voy a ponerlo.
Grabando. Y se pone en pausa, sí.
Yeah, I was saying that. It's just keeping on. But it's still, you take one submission per day.
Yeah, one flight,
Yeah.
one drone flight. Yes.
Hour.
Well, it's just one flight during the day. And so to have multiple points, you have to fly additionally
Per day.
per day. You can fly like, you can calculate ET at 11 in the morning, 12, 1, 2 p.m. And it extrapolates really nice.
Yeah.
So you can do multiple times per day, but also you can fly at different times in the year.
How much a part of the day? Flies the drone to simulate all the day.
To simulate, we tested the best. There is a window
Pero antes de este,
from solar noon, the
Yeah.
middle,
antes de este investigador.
2 hours before, 2 hours after So you have 4 hours where you can collect the data. If
4
you-
hours, it's about
From 10 to 2 p.m.
over 24 is 1 over 8.
Yes. We don't need, I mean, to get the daily ET, we just need to fly at midday,
Yeah.
only once. But if we want to validate extra points, we can fly every hour. You have extra points for validation.
Our service operators
Yes.
to extrapolate for the value and the restore,
Uh-huh.
you must
Pero,
have
¿en qué parte está?
so I asked how much for the day to validate.
Yes, you can.
Get about 1/3 of
Ah,
the
ahí está,
contribution you can.
Yeah, what's there or less, even less, because what's happening is the solar radiation is quite symmetrical. It's symmetrical. It's so
Let's think about 12.
yes. So if you fly at 12 or close, extrapolating is it's quite straightforward. Not much complication.
Speaking you and these guys take
Ya, descarado, descarado, no.
lots
Wow. Yeah.
Actually,
Yeah.
it depends on the presentation.
Are you, thanks for coming. Are you short on time?
No.
Okay. Because I was thinking voices can go and then you, but
Okay.
otherwise we can switch place.
Yeah, it's fine. I only have a poster. My last slide shows on my personal laptop at my house.
Okay.
So I just have one poster.
That's fine. Hey, ¿cómo estás? Hello. Nunca hace frío.
Afuera está
¿Qué más? Ya empezó el verano.
Oh
yeah, I forgot.
Iron it out.
I totally forgot.
Are you gonna grow it out?
Yeah.
Bro, I can live it another 2 weeks.
Another 2 weeks?
I'm traveling to California next week. And once I'm back,
Yeah.
I can share.
I think you should keep it.
Yeah, I'm thinking of that.
Makes you look like you're as old as you really are, not
Yeah,
like
now
12.
it looks like realistic.
Now you look Trent instead of really saying.
Oh yeah, kids, baby face. Oh man, I feel so cold, man.
Cold?
Yeah. The other guys
You nervous?
Probably could be.
Probably.
Pretty wrong.
Yeah, my slides are on my personal laptop at my house, so I just have like a poster. Is it on?
We can help with that.
No, like it's a just
When you can use it.
yeah, digital poster.
Pues nosotros vamos a conectar cada uno de estos laptops, entonces porque nadie tiene todas las situaciones juntas, ¿no?
¿Sí parece?
Y aparte sí.
Yeah, I need to look at it. I saw that.
Ahora voy a buscar dónde está.
And like, actually, we were gonna take that one.
I was hoping.
Yeah. Yeah, but it's in your name. Really? I mean, you should, you should probably talk to about it after some. It's your own. Yeah, it's good for a year. For a year. Yeah, that would be good, the right survey.
Yeah.
But United. Yeah, United was.
Yeah.
That experience, that Like Delta has green.
¿Cómo es Sticky Blinder?
Sticky Blinder. Ah, oh, ¿verdad? Es él, ¿no?
Sticky Blinders.
No mames, es Sticky Blinder. Ah,
Because like you go to. Yeah. Double check. Yeah. Because look, that's what you were on here. So I think it works.
es él, no mames, es él.
It would be worth
Y
checking.
ahorita
before you-
saca el gorrito.
Yeah.
Esta la chica. Wow.
But somebody in this. So he may. Yeah, that's gonna happen. But at least. Sometimes. Yeah. Yeah, it's okay. Yeah, because it was your. Dr. Alfonso?
Yes, sir.
I've got the question here. Yeah. You wanna, we're gonna get there.
Entonces, quería sacar el
أمير الراجل ده قال لي تعب السنة اللي داخلين السنة اللي داخلين اليونايتد قال لك على حاجة؟ لا والله.
Right. All right, everybody. Okay. We're going to continue the presentations, and now we're going to talk about almonds. Are almonds produced in Egypt? Yes. Los? Nuts. Yeah, nuts. Okay. So this project is about nuts. Okay. So Moises will be presenting his work on nuts and almond nuts using drone data.
Almond trees, nut trees. It's actually similar treatment. Sorry?
You have some?
Oh, no, now. I can give you later. Okay.
To distribute 1 kilogram for each.
Sure, I can show you some later. Okay. Okay, guys, I need your attention first. Everybody in the back. Yeah, thank you. We can go very fast on this because I know you're all exhausted, but this is very interesting. So you can see the same model application, but in different crops, because at the end of the day, the concept is still the same. We are just distributing in 4 different factors of energy. That's what we need, but it's in the small details. For example, we cannot use the same treatment that we did in grass, in almonds, that is nuts trees, right? So this project is getting held in California. We call it the Almond Project or T-Rex Project. I'm going to explain first the biggest scheme of the conception of this project. So California, we all know California because it's a technological hub, also because Hollywood, but also it's a monster in agriculture. Only the Central Valley of California holds 80% of almonds market worldwide. And that's how much is that? So imagine that every year, due to climate change, scarcity of water, and water use regulations, these farmers lose $2 billion every year. So there, I was looking at some questions, some interviews to some farmers in recent years due to climate change, how it affects them. And they say like they can own farms up to 200 to 1,000 acres, right? But suddenly, hey, you know, this month you won't receive the same amount of water as you received last year. And it's not like they irrigate less. No, they decide to cut fraction of their production. So it's not only losing production for that year, it's losing production for the next years. And every year they're losing $2 billion. So it's a billion market. They're moving a lot of money, but due to scarcity of water, they need to do something. So that's why these kind of projects that involves a lot of technology, they also need to receive a lot of fundings. And since then, the Almond Board of California gave initiatives to fund this project and working for the TISM model. Also, due to the scarcity of water, we need a more intelligent system to take decisions and irrigate properly the farms. And since then, the T-Rex project it was concepted by the Almond project, by the Almond board, the Utah State University, and the UC Davis of California, University California Davis. But what's the main goal of this project? What they want to reach is the real monitoring, the real crop monitoring that is not actually in the world that such a system like that or service like that. Because it's not about only taking pictures with satellites, it's about interpreting this information that we're getting from the satellites or from drones. So we can have the satellites and very specialized sensors collecting data, but behind we need to do more research on micrometeorological research, on physiological research. So we spread this work in 5 different teams. And USU, Utah State University team, we're working specifically on how to process the drone images we're collecting from field. And then at the end, the 5 teams that we're working in California and USU, we manage all together to share this information and then finally get a final solution for the real monitoring that we want to get. So once we get this drone data, you notice that, we have very accurate information. We need to obtain a lot of inputs for running the TSEP model, but there are some factors that are affected, especially for nut trees. In this case, we identify 4 factors that affect the TSEP model run. The first I'm gonna draw some trees here so I can explain this better. So which factors may affect my TSEP model run? The first one that we identify is which is the most appropriate time of the day to collect data. This is something you already heard before. So you mostly say that the best time would be solar noon because we don't have, we have high stress in plants, we have less shadows, but we know that the data collection from field can take some few minutes, but if we're collecting data from thousands of acres, hundreds of acres, it takes more than 30 minutes, 40 minutes data collection. So which is the window of time that we can take advantage during the day to collect data? Because out of this window of time, this could be 6 in the morning, this could be 6 p.m., which is the right time when we can start. And after what time we are getting a lot of bias, a lot of unnecessary data, right? So this is the first question. The second question we're solving is how sensitive is the TSEP model to the separation of almond interrow information? So we know that from drones information, we can get pixels of 5 centimeters, right? 15, but this is so small that when we get a map, how we can transfer or move that information from small pixels to a map of irrigation for the farmer, right? Because he may have like plot 1, plot 2, 3, and 4, but I cannot tell him, hey, here in this pixel, you need to irrigate this millimeters, and in the next pixel, another millimeter, right? So which is the better distribution to rearrange all of this information? So we are working with grids of information, which distance we have decided to work with the maximum distance among crops, which is 7 meters. In the case of grass, turf grass, how much distance it was? I think it was, we were working with 6 feet, right? Karen?
3 meters.
3 meters, okay. So in the case of almost interrow, we are working with 7 meters distribution. And how shadows impact the estimation of ET? If you can look at the pictures here, you can see that there is a lot of distance between 3 and 3. And when we're processing wrong information, we're collecting a lot of bias due to the shadows. So we need to filter that. We need to solve that before running the T-set model. So this issue needs to solve. We're working on that as well. And how well the performance of existing LAI models exists for ET estimation in almonds. So same case as Karen. Karen has to do a disruptive method to obtain LAI data from field. So there is a team in California, they are actually obtaining disruptive information from the almond trees. There is people that is collecting leaves from the specific trees and estimating a real LAI. But at the same time, we are taking measures with the LAI sensor. But they already exist some methods that we are approaching to estimate this in a very fastest way. So far, how much we have worked in this for objectives? First of all, to assess the most required range of time during the day, we're collating data at 3 different times of the day. This project, this is my first year in USU, but this project has started at least 3 years ago in 2021. Sorry, 2 years ago, 2021. Since then, every summer has been collected data in 3 different times. 10 a.m., which is about Landsat time. So we can compare our drone images with Landsat images. Solar noon, that is about 12 to 1 p.m. Solar noon. And mid-afternoon, because at some point in the afternoon, some previous articles suggest that there is at least in California, there is a high response to stress for crops, but for drone images, there starts to rise up the peak of bias that we're collecting. So we are searching about which is the most latest time we can collect data. And in this window, we are about to choose. Second is related to the grid I already mentioned to you. We have a distribution of very small pixels, but we need to rearrange this information. Third, the impact of shadows. We're running the T-set model without shadows filtration, and with shadows filtration is expected to get a more accurate estimation of ET when we compare the ET run model and the eddy covariance values model, because we also, as we have in interpret, we have a eddy covariance tower in field. The difference is about the height. I would like to show you a picture. I think I have it later, but we are measuring data of the eddy covariance towers about 10 meters because we have crops that goes from 2 meters height to up to 7 meters height. So we need about it. And finally, as I mentioned, LAI is a very time-consuming work. So we are validating some previous equations that were calibrated in 2012 by another team in California, also in almonds. So this research back then, they proposed 10 different equations from 10 different indexes equations, but only 2 of them are fitting enough well with high accuracy. The first one is the NDVI related, and the second is the near-red equation. With all of that, we may finally collect the. Karen, in her presentation, she shared with us her one by one correlation of eddy covariance tower and ET run by the T-set model, but she only had some few values, and it's because it's a lot of time, it's a lot of work to have to be done to finally collect one single value. This 1 point just means one full day of processing data. So imagine how much work we need to do to actually collect a lot of points. That's why it takes a lot of years and several campaigns of collecting data. For further work, we are currently going to California. We just came back 2 weeks ago from California, and we're going again next week to collect more data. Just some advantages we did is that we are working with a fixed wing that is collecting 6 images in just one day. So we're improving more our capacity of obtaining data in field. And I want to share with you a poster I prepared. All of this work we presented on November just corresponds to 1 day of processing. That it's mid-July of 2022. Just to obtain our NDVI correlations for ET estimations with and no shadows processing. And finally, what are the values we are getting? We're getting values here of ET. This is in watts per meter square. So this is before the long equation you did. And when we look at them, we have values that goes from 510 watts per meter square up to 540. 510, 540. That if we use the equation, we may get a value about 5 millimeters, of course. No, more than that, 6. What is that? Okay. So this is run by the model, but the covariance tower show us that we're getting a value about 560. Yes, it's correct. Yeah, 562. So we just got a difference about 50 watts per meter square, which is actually a bias that is held by the eddy covariance tower by itself. So we are in the right range, but for a proper correlation, what we need to do is at different times and different campaigns run of the model, and it may take more time. So that's all I want to share with you about the ALMOS project. We just started getting very accurate values, very similar to the eddy covariance tower. I still insisted that how important it is to understand these 4 concepts of how we are dividing the energy balance model. So you can collect high valuable data in field, so you can decide with what instrument you have in field and do a better job, right? Thank you, guys. That's all.
Questions?
I have 3 questions. Please, can you share this poster with us?
Oh yeah,
Electronic, it would be good.
Sure.
Second question, what about when we can use the outcome from the research to be applied because the end user is a farmer.
Yes.
And the farmer need a decision
Yes.
To save amount of water to maximize the productivity of each cubic meter. But we are still now as a researcher. What about when the California farmer was gaining the benefit from your research?
Okay. Yeah, that's a really important question. When all of these patterns, voices, scattering becomes a product that the end user, the farmers, the community of irrigators can benefit from it. There are 2 approaches. One, we do it all the work and give the data to them like OpenET. OpenET, you go to the website, you click, you can download, the farmer can download the data and make their decision. That's one way, and it takes a lot of effort and a lot of money. The second option is that we generate this science because the technology, the drone cameras, is commercially available. Companies like startups can take this information and start offering to the producers. So if we we cannot imagine a farmer flying the drone, processing the data, putting the IRTs, no. His time is more valuable doing other things. So what we see on the drones, it will come like a service that will happen from companies. They will build larger drones, more powerful drones that cannot fly one field by, let's say, 50 of them, lowering the cost of information per farm, becoming affordable to the farmer. Right now, still the technology is expensive. Takes a lot of time. How many students we took to do one drone flight? Several of them. We need, so how the science is progressing is, do we have a good equation for LAI so we don't have to collect data anymore? Do we have reliability on the two-source energy balance model so we don't need to be checking it again against an eddy covariance or a lysimeter? So we're building that confidence on the models, so will become ready to be used for anybody. So it will be like OpenET. You just go to the website, you trust the data, and you make decisions like that. So we don't. There are, as I said, two approaches: academia doing all the work, or letting companies take that science and making it available to the producers.
So it's all is applicable and farmers did this in their management report.
The interesting thing about California, when we talk about California, we talk about Google and big companies, big technological companies. These farm companies also have their laboratories, their research laboratories. They are already using satellite data to make decisions about their crops, because for them, any 2% improvement in productivity is millions. So they invest on people, hardware, computers. So they are waiting for the drone science to become very reliable. So they will start using that data for their management. Right now, they're using all of them. The large California are using Landsat data. They already have their system, their code. So this laboratory inside the company, instead of sending pixels to the managers, what they say, they send commands. For example, the GIS laboratory says, okay, manager number 52, tomorrow irrigate field A, B, and C for 3 hours.
Yes.
That's all the information the manager of the farm gets. He doesn't get pixels, he doesn't get analysis, just a command. That's what they're doing in these companies.
Yes.
So what does it mean now for the smaller producers? Okay, this is large companies that have the money. So the idea, maybe a naive idea, is that they can also get together, that the small producers can become an association of producers, and a company can offer these services on an internal website that they can access and check their fields, and they pay for the service. So that's the hope. That's where we believe all this science is going to go.
So
They should also get
I was gonna just add real quickly, do you see that as private sector, or you don't think like the Soil Conservation Service or something like that would take over that responsibility?
It will be up to them. We have, in this case, we have NASA took responsibility, and we have OpenET. So NASA is right now producing ET data for half the country already. So, but the question for them is that, okay, we are going to receive money to build the system, but we need money to continue the system, and that money, that right now they're figuring out how much do I need to charge the user of OpenET that he consider paying and not getting away? So they're right now in that dilemma. So they're trying to figure out what's going to be the cost rate, because these large companies in California, they want the OpenET data. They want direct connection to the servers of OpenET, and they do their GIS, their summary, and I mean, for them, again, 2% increase in productivity, it means millions for them. So they want that. OpenET hasn't figured out how much to charge yet. But a company also will do the same. To provide a service, will say, okay, if you want to pay per month, this is the amount. If you want to pay an annual license, this is the amount. And there are companies that are already doing this. I'll mention that tomorrow, but have you heard of EasyWatch?
Yeah.
EasyWatch. Yes, they is one of the ET models that also they're estimating soil moisture and other variables, and they're offering to producers their service, their data. So that's what's going to become. All this science will become part of a company.
Yes. Question. Is this the maps used by drones or by Landsat?
This drone.
Those are drones.
The resolution of that map is 1 pixel is 1 tree. So there are, I don't know how many trees, but and this is flown with this large drone. If we fly with the copter, that the one that we use for our exercise, it will be one field, one. But this drone, in the same time that the helicopter fly this one, it flies all of this. That's the. So as technology of the drone progresses, the cost of collecting data decreases. So the fixed wings are one potential solution to reduce the price of getting data.
And how to make this maps shadow free?
Shadow free?
Oh, we work on a. So for running your teaser model, you remember you were taking a lot of time, right? You had to do a lot of clicks. You have to be very organized on your inputs. But for that, we are already working with Python code. So what I do is arrange my drone images with a certain code, and I only process, and I only have to do just several clicks, right? Tick, tick, and it takes from 10 minutes to 30 minutes to process all the inputs I need for the teaser model. But we spent several months to work on that code, right? It's a very long code. Sorry?
The mechanism.
Oh, the mechanism is.
What is the idea?
The mechanism is like this. If you have a tree, okay, the drone data produce a 3D reconstruction of the tree. So we have what we call it a surface digital model, a DSM, a digital surface model. So what we do is we play with the sun angle. Shadow. This is shadow. Yeah. So depending on the time we fly the drone, we use this 3D reconstruction to reconstruct the shadow. And these pixels, okay, are eliminated from the analysis. So if we are at solar noon, we basically don't have any shadow, or maybe 1 pixel of shadow. So we play with this movement, the movement of the sun.
There is a tool
that the shadow is eliminated.
Yes.
There is a tool in ArcGIS Pro that is called Hillshade. So in Hillshade tool, you only put the azimuth value, the azimuth angle, and I think it's the latitude angle also. And you need to put as an input your DSM, that is the digital surface model. You obtain that from drone image processing, photogrammetry, right? So this azimuth.
Yeah. So it's a tool already existing in ArcGIS.
And it obtains all the shadow you need.
we apply that technique to eliminate the shaded pixels. The shaded pixels are raw data. The shaded pixels have a weird spectral signature. It like bare soil can have an NDVI close to 1 in shadow. So it distorts our algebra, our understanding. So because it does that distortion, for us, it's like better to throw it away and reduce our uncertainty when processing the data for evapotranspiration.
There is something I want to add. That is, we are very strict when we're trying to reduce the bias from the images. So we also additionate another threshold, another filtration, and it's the height filtration. Because since we have trees here, drone processing give us the DSM. DSM, digital surface model, is a first run of the photogrammetry work, and it just represents the field with the trees, right? But if we do some additional work to this product, we can obtain only pixels from the field, and we can reconstruct a DTM model, as a digital terrain model. And since we have both of them, we can extract and make a map of only height, because DSM minus DTM will give us a height map. Height map, right? And since we have a height map, we know that our trees go up to 8 meters sometimes, but we have a minimum value that we have decided to work a minimum value of just 1 meter. 1 meter. So anything below 1 meter height, where is the shadow, we filter that, right? And it also works properly. Yeah, it does a good job. So yeah. So we are comparing all of this modification we're doing to the inputs, and then we run the TSEP model, and we are comparing which run got a more accurate and more close value to the real one that we got from the EDICO variance tower. Yeah. That's another question.
Is any of this being done by AI yet?
AI, the Liferia index. The Liferia index, for example, we collect LAI on this location, okay? And we can develop equation using a vegetation index. Good. But if we go to another variety of outputs, the equation might be slightly different. So having a universal equation is kind of so what we do is, okay, let's let the machine learning decide or create a model that can predict the biomass anywhere. But we give them data from different locations, different varieties, different times. We just let the machine decide if I need red, green, and blue. Sometimes it needs height, sometimes it needs the width of the category. So we generate these maps, like what we call it general LAI models using machine learning. So we did that for vineyards. So there are vineyards that are tall as 2 meters. There are vineyard plants that are just 1.5 meters. Others that are planted closely. Others that are planted more separately. So in every location, the equation is different. So we say, no, too much chaos here. Let's give all the data to the machine learning and let the machine come up with an equation for any location. So it came up with a model that now we can use it anywhere that these grapes are produced.
Thank you, guys.
Thank you.
All right, thank you very much.
Oh, no, sorry, I was erasing this. Do you think you can share that picture to the group later?
Yes.
Thank you.
You did? Yes.
You need to pen drive?
Yeah.
Here, I think.
Yes, 1 second.
Okay.
How's it going? Hi.
Welcome back.
Thank you. So I had a really nice slideshow from the conference I recently presented at, but the slides were on my personal laptop and I totally spaced that, and my personal laptop's at my apartment. So this is the next best thing I had, so I apologize. But this is just a quick poster I made on my research that I used for a presentation a while ago. And so my research is on quantifying the uncertainty of ET and irrigation plot scale research. And so how we're doing that is, if we look at the picture here, these two stations, I have canopy sensors on both of them that are enough to run the two-source energy balance model.
Take it off the presenter mode.
Yeah. Yeah. Yeah, sorry if it's hard to see. So these two tripods here have arms. They're a little bit difficult to see because in the picture they're sticking right at you. But on them they have several remote sensing devices that allow me to run the two-source energy balance model in order to find evapotranspiration. And then below ground, all these yellow wires that come up this conduit right here are soil moisture sensors. And so I have them below the ground in this site, and then over here, right here. And they range from a depth of 3 inches to 54 inches in a vertical profile. So we can use a water balance in order to find evapotranspiration that way. And so when you compare the two, you can start to quantify the uncertainty between the two. On this is the irrigation system back here in the picture. And so it's just a wheel line that runs across the entire field. And on it, we have an event logger. And so that we know the irrigation inputs. And then this big tower over here is an eddy covariance tower, which is ran by another professor in a different department. But we can sort of validate some of our data against his data. And he also has, you can't see in this picture, it's back here near the building, but he also has a weighing rain gauge. So we can have the precipitation data based off of his data. And so then I have some of the results from last summer here. So on the arm that sticks out over the canopy surface, it has a IRT thermometer, which finds the temperature of itself and then of its target. In this case, the target is the soil and vegetation mixture. When the canopy grows tall enough, obviously it's just the vegetation, as it can no longer see any soil. But we can start to see some trends here. So the bottom is the date. Sorry, it's in the month day format and not the day month. I think that's what you guys use. But you can see throughout the summer, there's sort of a negative downtrend. This is, of course, because it gets cooler as we get closer out here towards November than it is over here in June and July. We can also see some spikes in the temperature, and that is because the field crop we are using is an alfalfa grass mix, so it's used for hay, and they have multiple cuttings every year. So the spikes here are when they cut the vegetation, and the thermometer can see more of the soil than it can vegetation. So of course the temperature is going to increase because the soil temperature is warmer than the vegetation increase. So this is huge bump right here at the end of July, beginning of August is second cutting. And then this one right here is their third cutting, and they only got 3 cuttings off the field that year. First cutting was already performed when we had the sensors in the field. And then down here is the calculated NDVI. And NDVI is an index that represents the green biomass that the sensors can see. And so 1 is the most, 0 is the least. And so this line right here is the fully sort of bloomed alfalfa. And then this dip right here is, if you look at the date, it's at the beginning of August again. It corresponds with that spike in temperature. And that is because that's when second cutting happened. So of course the NDVI sensors are seeing less green biomass. And so there's a dip in the NDVI index. And then this dip over here is third cutting. And then as the plant starts to go dormant here at the end of October, beginning of November, we start to see it drop off as well. And then, so this sensor works based off of incoming radiation. And so some of these days right here and right here, where you see some anomalies, those are probably due to super cloudy days or maybe even a bird flying over or something like that. And then those soil moisture sensors that I spoke about, here's the results from the deepest one at station 1. And so as you can see, we have some anomalies, these big gaps in the data here where we're having some battery issues. But you can even see here it's not a perfectly straight trend line, which is interesting to look at because oftentimes when we do evapotranspiration modeling, we assume that deep percolation is equal to 0, which probably is true over an entire watershed basin or a huge watershed area. But when you scale down to the plot scale where water is really managed at least on the agricultural level, it's not. It can sometimes be not true, which the data kind of indicates that it's not true in this case. As you can see, it's not perfectly straight. So we currently have these 2 stations back out in the field. The second station, the one in the back, is being moved around. I'm headed out there tomorrow actually to move it to a different location. So we're moving it upwind and downwind both of station 1 to try to be able to calculate the covariance for the wind on the field. So I think that's all I have for you. I'm sure there's several questions though. If not, that's okay too.
Did you, when you measure the temperature of the earth, like Landsat or?
So it's a remote sensing, yeah, and it's an infrared thermometer, and so it just sits on the tripod arm.
Skin temperature.
Sorry, what was that?
Skin temperature. What is the name of temperature? What is this type name of temperature?
Oh, it's referred to as an IRT, which stands for infrared thermometer. And so on these tripods here, they have an arm. It's a little bit difficult to see in the photo because it's like sticking straight out at you in the photo, but this bracket here, it has an IRT on it, and it can see straight down of I think 0.9 square meters of ground, and it takes the temperature from that soil vegetation mixture, and then obviously as the crop grows, it can only see the vegetation.
Also, can you send us this poster? It's a poster?
Yeah.
Okay, please share with us.
For sure.
Cost you $10.
You publish it before. It's just a poster. Many people say it. It's free.
You have to pay Dr. Aziz.
It's free.
You. Dr. Aziz.
I have a question for you, since you've become experts on NDVI, right? I show you a table. Okay. What's the condition of the vegetation at 0.4? NDVI, you are experts on NDVI. This is exam for the certificate tomorrow. Okay. We got a table, right?
Yeah.
We said 0.4 and 0.7. We define the limits.
0.4 is low vegetation.
Yeah, bare soil. The view has a lot of bare soil. And you see, look, is that the harvest?
Yes.
You see that value. Now, 0.7 is around here. So this is a really nice representation of the variability of the NDVI from ground or ground-like conditions all the way to maximum cover of vegetation. So it's a really nice example of how NDVI changes.
Alfonso, can we measure or can we calculate the NDVI without drone, without
This
from
is a
them-
this is a sensor.
yeah, I mean if we can calculate the NDVI from the sample, take a sample from the soil at different depths, and if we didn't have a sensor, if we didn't have a drone, if we didn't have a Landsat data, it's really many countries over the world,
Yes.
they didn't have. They cannot use the Landsat because they don't have the. Can we collect a sample, a field data, and we make some?
All right. It will be very hard. It will be there is what is called the land assimilation models.
Mhm.
It's a very complex models that look to do water balance, energy balance. Those models
Mhm.
are run for like 1 pixel is a kilometer.
Mhm.
Okay. And internally, they can estimate or approximate the amount of biomass.
Mhm.
There are such models, but just to run the model, it's cheaper to get a drone than run the model.
Mhm.
So it's too complex.
Yeah.
Yes, it requires a lot of effort just to calibrate the model so
Yeah.
it can give you a good results.
Good.
Any questions for Sheridan? All right, thank you, Sheridan.
It's the last one.
The last presentation of the day before
We have an hour.
before your homework.
Ready?
Yeah.
We have an hour. To finish at 5 o'clock.
Well, how is the workshop without homework?
Yeah. Without homework, yeah. 9. I will go with Alphonse to the hospital.